Hello, chemistry students. In this video, we will discuss atomic spectra or line emission spectrum and the Bohr model and how it was derived based on these observances. So when atoms or molecules absorb energy, that energy often is released as light energy. We see this in fireworks and neon signs. So typically with a neon sign, you have a discharge, a gas tube that you input energy in the form of electricity, and the electrons and the atoms are excited and what to higher energy states, and what goes up must come down. We learned that with kinetic energy and potential energy. So once they're excited and they drop down to lower energy, they release it in the form of light. And typically, light emissions can be used to identify the different elements. So we see this in really easy flame tests that we can do in labs, where we can take a solution that has the ion, let's say, of a metal, and put it under a flame and observe the different colors to help identify that element. And a lot of times this is used for qualitative analysis and identifying an unknown. So with the atomic spectra, when emitted light is passed through a prism, right, which has a diffraction grating, a pattern of particular wavelengths of light is seen that is unique to each type of atom or molecule. So that pattern is called an emission spectrum. So typically you can take the hydrogen discharge lamp, again, have a slit, an opening that is proportional in magnitude as the wavelengths of light. It bends and diffracts, and when we see that it bends, we also see that the longer wavelength, red, is further away from the shorter. So this is the longest, and this is the shortest wavelength. And so for hydrogen, we see that there's 4 lines in the emission spectrum. Now, the longer the wavelength, the greater the angle of diffraction. This is seen in Bragg's equation, where wavelength is directly proportional to theta, which is the angle. And again, because red is a longer wavelength, there is a larger angle of diffraction, or you can think of it as a larger separation from the other lines in the emission spectrum. The shorter wavelengths, like violet and blue, are closer together. So here are some examples of spectra. What I want to show you is, as the elements get more complicated, and what I mean is having more electrons, we start seeing more lines in their emission spectrum. And when we compare it, however, for all the elements, we see that their emission spectrums are different than visible light, white light. And when we look at white light, it's a continuous spectrum, like a rainbow. We don't see that with elements. We see discrete lines. So the individual lines were key to the formulation of Bohr's atomic model. So the movement of electrons were the reason the atoms are emitting light. So as they absorb energy and go to higher states, when they drop back down, they're emitting light. But why lines? Lines mean only specific wavelengths were allowed. So that means only specific amounts of energy were released. Otherwise, it'd be continuous. So an electron can change energy level, again, by absorbing energy to go to a higher state, or they can emit energy and move to a lower level. And we see that in this example. Now, the energy levels, you can think of the n as what's referred to, and we'll learn this with quantum numbers, the principal quantum number. It's also the energy level. If you look at a periodic table, it's the rows or the periods. So hydrogen and helium, they're in the first row, that's energy level 1. You move down, second energy level, second row, second period, that means they have 2 energy levels, 1 and 2. These energy levels are just regions of space. So if I take hydrogen, it has an electron in energy level 1. Again, these energy levels are just regions of space. So if energy comes in and excites the electron to a higher state, it can be excited further away from the nucleus. You can think of as the proton in the nucleus and the electron are attracted to each other. It requires energy to separate it. That energy can come in as electrical energy or some other form of energy. But again, over time, the electron, if it's in an excited state, wants to relax. It wants to go back down to what's referred to as the ground state, where it belongs, just like we belong on the ground. So when it relaxes from an excited state to the ground state, it emits a photon of light because energy must be conserved. That's the law of conservation of energy. We learned that as the first law of thermodynamics. So it releases that in the form of electromagnetic radiation or light. So with Bohr's model, remember when we saw that line emission spectrum of the hydrogen lamp, we see that these distinct lines are specific to certain emissions. So the longer wavelength, right? Remember, longer wavelength means shorter frequency, and shorter frequency means less energy. And we know that because energy is directly proportional to frequency. And we learned that energy is equal to Planck's constant times frequency. So shorter frequency, less energy. So red, this line red right here at 657 nanometers is a transition from the third energy level down to the second. When we go blue-green, it has a little more energy because it's a shorter wavelength. We can see that it's a shorter wavelength. So it has a bit of a higher frequency and is more energetic. And that's because instead of from 3 to 2, it's falling from energy level 4 to 2. And then violet is 5 to 2. Now, if you look at a hydrogen emission spectrum, there's actually 4 distinct lines. What's interesting, in labs, some students only see 3, but some see the 4th. And the 4th would be the most energetic. It would be coming from an energy level of 6 all the way down to energy level 2. And that is seen at the far end of the visible region at 410 nanometers. Remember, the visible region is roughly 740 nanometers to 390 nanometers. So it's always interesting to see some students not seeing this 4th line. So when we have a discharged lamp and we excite the electrons, they have to drop down. So the transitions from the excited to the ground state emit these lines. Now, the emitted photons have energy, and it's corresponding to the difference in those energy levels. So you can think of the delta change in energy is proportional to the change of the final energy state and the initial energy state. So photons' energy will appear in a spectrum based on their wavelengths, and we can actually calculate these energy levels with something referred to as the Rydberg equation. And the Rydberg equation is the reciprocal or 1 over wavelength is equal to Rydberg's constant times 1 over the energy level squared minus 1 over the energy level squared. Now, what does energy level N1 mean versus energy level N2? So first, the Rydberg constant is in per meters, and that's because of wavelength. And you have to, if you don't do this, if you don't make the N2 the larger energy, this value doesn't work. You have to, or you'd have to take an absolute. So to make this easier, you're going to make your N squared in these particular problems bigger than N1. So this is from the excited state. You can think of that as your initial state, and it's falling down to the ground state or a less excited state, a lower energy level. So let's just do a problem. So a spectrum for hydrogen shows that there is a relaxation from N equals 6 to a lower energy level. So right off the bat, this is going to be my N2 because it's going to be greater than my N1 because the N1's lower in energy. The wavelength of the emitted light is 704 or 7,460 nanometers. So this is not in the visible region, right? The visible region is 390 to 740. So this is a much longer wavelength. So it's not going to have as much energy. But the whole goal of this is to find the lower energy level. So we're going to use Rydberg's equation. We're going to plug in the constant, and we know that N2 is the larger number because that's the higher state, and we want to find what is the lower state. It's 7,460 nanometers. We convert that to meters using 1 meter is 10 to the 9 nanometers. And we plug everything in. And again, remember the N2 is the 6. So then we're going to square that and get 36. We're going to divide both sides by Rydberg's constant. We get this number, and we see that the meters cancel. So this is unitless for the energy level. And now we're going to add 136 to both sides, and we get this number. And then we're going to solve for N1. That's squared, so we have to take the square root, and we get it falls down to the lower energy level of 5. So this transition was from the 6th to the 5th energy level. So not a lot of energy was released. So Bohr's model. The electrons travel in orbits that are fixed distances from the nucleus, and they're stationary states. They're stable. The energy of the electron is directly proportional to the distance the orbit is from the nucleus. So electrons emit radiation when they drop down from higher states to lower states. The emitted radiation is seen as a photon of light. So the distance between the orbits determines the energy. So what we can do is we can say, well, that photon of light is equal in magnitude, opposite in direction, but equal in magnitude as the energy of the electron as it's releasing that light. So the photon of light is equal to the difference in energy of the electron as it transitions from N2 to N1. And Rydberg's allowed us to calculate that. But now what we want to do is we want to determine not just the energy levels, we want to determine the amount of energy. So we can combine Rydberg's equation that we just did, which allows us to determine to what energy level it drops down using the wavelength, to actual energy, quite simply, by remembering that the energy of a photon is Planck's constant times the speed of light over wavelength. And that, again, was derived from Planck's, or energy is equal to Planck's times frequency, and rearranging, substituting for frequency, speed of light divided by wavelength. So we have to get a new R, though. The Rydberg constant doesn't allow us to get the energy of a photon. So now we see that this Rydberg constant is specific to the hydrogen atom's energy. So how do we get that change? Well, we come up with a new RH, a new constant. So instead of this Rydberg constant, if we want to do it in terms of energy as opposed to the reciprocal of wavelength, it's 2.179 times 10 to the minus 18 joules. Now in your book, this is the more common calculation. However, if you were in lab, you would be using this. How did they get from Rydberg's constant to the constant for RH for the change in energy of electrons? Well, what is the difference? Remember, we're kind of setting this equal to 1 over wavelength. When we're using RH, we want to set it equal to energy. Well, how do I get this equal to energy? I have to times this by Planck's and the speed of light, and then that would equal energy. So we take Rydberg's initial constant, I times it by the constant of Planck's and the speed of light, and I end up getting the 2.179 times 10 to the minus 18 joules. So there's a few equations you got to be familiar with and a few constants. So speed of light is equal to wavelength times frequency. The speed of light is roughly 3 times 10 to the 8 meters per second. Energy is equal to Planck's constant times frequency of light, and Planck's is 6.626 times 10 to the negative 34 joules second. We learned earlier that you have a Rydberg equation with a certain constant. That is very useful if you have wavelength and you only want to find energy levels. And you have to make sure that N2, because it's going from a higher state to a lower state, is always the bigger number. Now, if you want to solve for energy, what we can do is we can use a new Rydberg constant, RH, and plug that in, and then we'll just always use the absolute for that transition. So you might see in your book this example where they show negative RH, and then they show negative RH over 4, negative RH over 9. What this is showing you is the energy levels. And here's my nucleus. And the first orbital, or the first orbit where electrons are located, would be N1. Further away is N2. Further away is N3, and 4, 5, 6. Eventually, you would reach N infinity. And what N infinity represents is when you're actually removing an electron. So we learned in the photoelectric effect, that's referred to as the binding energy or the work function psi. You can also think of it as the ionization energy, the energy required to remove an electron from hydrogen and make it an ion. So when an electron is ejected, basically the final energy state is infinity. So if we plug it in to that equation that we just derived, and we're trying to figure out the energy of the electron, we put in Rydberg's constant, we put the final state infinity over 1, 1 over infinity squared is approaching 0, so we put a 0. We get a negative 2.179 times 10 to the minus 18 joules. Take the absolute. So to remove that electron would require that much energy. And that makes sense. So to remove an electron in the first energy level requires 2.18 times 10 to the minus 18 joules. And that would be positive energy because you're putting it in. And that would bring you to what is referred to an energy of 0. And that confuses people. Why? An energy of 0 is actually higher in energy than the energy level of the ground state when this drops down, which is actually a negative 2.18 times 10 to the minus 18 joules. So this is actually more stable because it's lower in energy. It's negative, not 0. So they do this to help you understand direction also. So you'd have to put in, to go in the opposite direction, a positive amount. Now, what about the energy to remove an electron if it's in the second energy state? How do I figure that out? Well, I just take the N2 and I basically take my RH and 1 over N squared. So what do? If I'm in the second energy level, 2 squared is 4. So it is 1/4 the energy it would require to remove an electron from the first energy level. If it's in the third energy level, it's 1/9. So what we see is the biggest distances between the first and the second, then the second and the third, and then these distances get smaller. So it gets easier to remove an electron as the electron is further away from the nucleus. So it requires less energy, which totally makes sense. So in the book, you'll see this. This shows how much energy required to move it from the second and the third, and we see it's less and less energy. Now, we're talking the amount of energy to remove it from, one electron. What if I wanted to remove a mole of electrons? Well, I'd have to use, again, Avogadro's number. So joules per photon. So this would be the amount of joules I would need per photon to remove an electron. And then, of course, there's 6.02 times 10 to the 23rd photons per 1 mole. And I can convert joules to kilojoules, and I get 1312 kilojoules per mole of electrons. That's the amount of energy required to remove a mole of electrons from hydrogen. Later, when we learn ionization energy, you will see this value on an ionization energy table. So when we were looking at the line spectrum, we were just seeing transitions falling into the second energy level. Why? Those happen to be within the visible region. Those energy differences, so again, from third to second was the least amount of energy, so we saw the longest wavelength of red light. Then we went from 4 to 2, and then 5 to 2. They're actually missing 6, but there is a 6 to 2, which was the 410 nanometers. All of these fall within the visible spectrum. However, if it was to fall all the way down to the first energy level where it belongs to the ground state, those emissions are higher in energy. We can see there's a greater distance. So that is a much higher frequency. So these energy transitions are higher frequencies, which means they have shorter wavelengths. And what's shorter than visible light? Ultraviolet. Just like the transitions that are only to the third, right? They're less energy, so they're lower in frequency, but longer wavelengths. And what's a longer wavelength than visible light? Infrared. Now, these are actually referred to as series. So when you're studying emission spectrums, there's different series. The Lyman series is the ultraviolet, and that's when the hydrogen electron drops all the way back down to 1. When we work in a lab and we use a spectroscope and we're only observing within the visible region, because that's what we see, and we look at those line emission spectrums with the nice colors, that's the Balmer series. And then if it was infrared, which we can't see, but we can use thermal energy, that would be Paschen, and so on and so on. So what line emission spectrums allow us to do is to calculate energy levels for the hydrogen atom. It is a very good indicator of telling us the difference between these energy levels, and it can be supported based on the wavelengths of light that we see in the line emission spectrum and calculating those energy transitions. What we'll realize is that Bohr model, it only works for single electron species. However, it was a critical model in the understanding of how light and electrons and how light can help us understand the atomic structure and the location of electrons in atoms. And it was a bridge to the greater understanding that we will be seeing in quantum mechanics with the multi-electron species. So I hope you enjoyed the video. And as always, leave your comments, or if you have any questions, go ahead and email me. Thanks for watching.